Welcome to the Wright Science Daily Revision Boost. First of all, congratulations to our top 3 scorers from Day 13's quiz, which were Ravina and Bamidele, Aoife and Molly. Well done folks, let's keep it up. Today's daily formula is for power. So power in watts is the potential difference in volts times the current in amps, or current squared in amps times the resistance. In today's biology blast, we're going to have a look at the start of the endocrine system. So the first thing we need to know is that hormone is a chemical messenger. Make sure you know that definition. And they're made in these endocrine glands. Once they've been made, they travel through the blood in the plasma until they reach the specific cells in their target organs, which then causes a response. You need to be able to compare the hormones and nervous responses. So if we think about hormones first of all, they're fairly slow but long lasting. They travel as chemicals in the blood and they target a much larger area. Whereas when we talk about nervous control, it's fast but short lasting. It travels as an electrical impulse along the axon of a neuron and targets a very precise area. When we refer to the phrase homeostasis, this is the maintenance of a constant internal environment. And what we actually find is that we use hormones to control these processes that need that constant adjustment. When we refer to target cells, these are the cells within the target organ that have specific receptors on the membrane or in the cytoplasm for that specific hormone. So that once the hormone binds to the receptor, the target cells will produce a response. For those of you doing the higher tier, then we need to know about negative feedback. And quite simply, negative feedback is a type of control mechanism that's used in homeostasis, where a small change in one direction is detected by the receptors, and then the effectors work to reverse that change and restore the conditions to their normal level. So you've got a little flowchart on the right there just showing you how this works. So the change is detected by a receptor, we then bring corrective mechanisms into effect by the effector, the conditions are returned to the set point, then the corrective mechanisms are turned off and the conditions in the body change from that set point to be detected by a receptor, and round we go again. The first example we need to know of negative feedback is thyroxine. Thyroxine is produced in the thyroid gland and regulates the metabolic rate of the body. So the thyroid gland takes iodine, which comes from the food, and converts it into thyroxine by combining it with the amino acid tyrosine. So what we actually find in terms of our negative feedback system is at the bottom there. So the hypothalamus detects the low level of thyroxine in the blood. It then triggers the release of TSH by the pituitary gland. The TSH stimulates the thyroid gland to make the thyroxine, and then the hypothalamus detects the normal level of thyroxine in the blood. So the pituitary gland stops making TSH, which means the thyroid stops making thyroxine, and then eventually we get back to the situation where the level of thyroxine is lower, which is detected by the hypothalamus again. The second hormone we need to know about is adrenaline, which is produced in the adrenal glands, and it prepares the body for the fight or flight response to stress. So a few things that adrenaline will do: it will make the cells respire faster, it increases breathing rate and heart rate, and it diverts blood away from areas like the digestive system to get the blood to the muscle so that they can work more efficiently. Quick reminder of our daily formula: the power in watts is the potential difference in volts times the current in amps, or the current squared times resistance. In today's chemistry check, we're going to have a look at the reactions of acids. So carbonates are ionic compounds that contain the carbonate ion, which is CO3₂-. And we need to know the general word equation, which is the methyl carbonate plus acid makes salt plus water plus carbon dioxide. You can then use that to substitute in whatever methyl carbonate and acid you're given in the question. We need to remember that most carbonates are insoluble in water. The soluble ones are the group 1 carbonate and ammonium carbonate. Everything else, insoluble. When we come to actually want to prove that we're making carbon dioxide, we need to know the test for carbon dioxide, which is we bubble the gas through lime water and it goes from colourless to cloudy. The second type of reaction we need to remember the general equation for is metal and acid, which makes a salt and hydrogen. Again, substitute in the name of the acid and name of the metal, and then you can work out the salt. When it comes to testing for hydrogen, we need to remember that that is a lit splint making a squeaky pop sound. For those of you doing the higher tier, you need to know about hydrogen ions and the pH. So hopefully you remember a solution is a solute dissolved in a solvent, and the greater the amount of solute that solvent contains, the greater the concentration. So if you remember, a dilute acid contains a low ratio of acid to the volume of the solution, whereas a concentrated acid contains a high ratio of acid to the volume of the solution. When our acids are in an aqueous solution, they release hydrogen ions. And what we mean by that is the covalent bond breaks between the hydrogen and the other part of the substance to form a hydrogen ion and a negative ion. And obviously that negative ion depends on what acid we're talking about. The strength of an acid is determined by how many hydrogen ions are released, or we refer to this as how ionized it is. So a weak acid is only partially ionized, so that means only some of the hydrogen ions are released from the molecule, whereas a strong acid is fully ionized, so all of the molecules have released their hydrogen ions. Make sure you don't mix up strength and concentration, they're two different things. When it comes to linking pH with the hydrogen ion concentration, when the hydrogen ion concentration increases by a factor of 10, then the pH of the solution decreases by 1. So what we find is a strong acid has a lower pH than a weak acid at the same concentration, but when an acid is concentrated, it has a lower pH than when it's dilute. So remember those two key patterns there. So we use a pH titration curve to show the effect on pH of changing the hydrogen ion concentration during that neutralization reaction. So you can see the volume of acid along the x-axis, the pH of the mixture on your y-axis, and that vertical drop is the point at which neutralization occurs. So this is just a standard titration, which hopefully we remember from our chemistry. We put 25 centimeters cubed, for example, of dilute alkali in a beaker. We estimate the pH using universal indicator, or we use a pH meter to get a more accurate measure. Add 1 centimeter cubed of dilute acid, stir it, record the pH, and we keep repeating this until we've added an excess of acid, and we plot our results on the graph. Hopefully we still remember today's daily formula, which is the power in watts is your potential difference in volts times the current in amps, or the current squared times resistance. In today's physics prep, we're going to have a look at atoms and isotopes. So hopefully we remember that the nucleus of an atom is made up of protons and neutrons, which are two of the subatomic particles that make up an atom. We do need to remember those key facts about our three subatomic particles. So protons, relative mass is 1, their relative charge +1. Neutrons, relative mass of 1, relative charge 0, hence they're neutral. And the electron has a relative mass of 0.0005 and a relative charge of -1. So do remember that the charge on the nucleus depends on the number of protons present, and because it's the number of protons that are present, it will always have a positive charge. When we're talking about an isotope, it's an atom with the same atomic number but a different mass number. And the reason for that is because it's got the same number of protons and electrons, but a different number of neutrons. And the way we write their name is given there, so carbon-12, carbon-13, carbon-14, those are three isotopes of carbon. And obviously the number after there is representative of its mass number because that's the one that's changing. So when we're given that, we can work out the number of protons, electrons and neutrons. For the protons and electrons, just write down the atomic number. And then for our neutrons, all you do is the mass number minus the atomic number. When we're talking about the atomic number, that is the number of protons or the number of electrons, because they're the same in an atom, remember. Whereas the mass number is the number of protons plus. Final reminder of the day for our daily formula: the power in watts is the potential difference in volts times the current in amps, or current squared times the resistance in ohms. Now we've had a quick recap, then head on over to socrative.com and test your knowledge on the topics from today. The room name you need to enter is Wright 2662. Good luck! So as always, if there's been anything that we've run through on this daily booster that you're not 100% certain of, head on over to the main playlists to get a little bit more of an in-depth discussion on them. So for biology, it's the B3 playlist, chemistry, the C3 playlist, and for the physics, it's the P6 playlist.